All right. So for this assignment, what you're going to do is you're going to simulate what you've learned in caches, right? So I just pulled up this diagram here because I don't have a document to show the diagram to draw anything. So just let's assume that we have so many different sets, and each set is going to have many different lines. And what kind of associativity is it? Is it direct mapped, set associative, fully associative? What kind of cache is this? When you have multiple sets and each set has multiple lines in them. It's a set associative mapping, right? Okay. So all right, so we have the valid bit, and then we have the tag, then we have some bits to indicate the block. So you guys know that structure, right? The last few bits is for the the particular byte in the block, and then you have the number of bits, some bits to represent the set number, and then you have the rest of the bits to represent the tag. So that's the same structure that we'll be following here. So when you talk about cache hit and cache miss, what does that mean? Can you guys give me a quick summary of that? It's okay. Yeah, go ahead.
I mean, if the data is in the cache, then it's a hit, and if it's not, then it's a miss, and you match the valid bit and
the tag, right?
The tag,
yeah. Sure. So initially, you won't have any data in these sets, right? It's all going to be empty. So whenever you're going to bring in the first data block, that's going to be it's going to be a miss initially. So you'll bring in the first data block to cause a hit, right? So initially all your valid bits or whatever it is going to be 0, and then when you bring in your first block, it would be set to 1. You would set the tag and so on. So as you said, you would match the valid bit, you would match the tag. You would see if the valid bit is 1, you would match the tag, and you would match the set, and then you would retrieve the block if it is there, which we call it as a cache hit. So I'm sure Gerald has taught you guys about all of that, but just wanted to refresh that quickly. So that's called line matching and block selection. And then we have, so in this assignment, we are going to do the least recently used replacement policy, which means that if you're going to have, as we know, we are going to have multiple blocks in the set, and when we want to bring in one more block into the set, we would have to replace some of these existing blocks. And what would we choose to replace? We would choose to replace the least recently used block. So I hope you know about that too. Sure. So now let's just go through the assignment spec that we have. So did any of you try unzipping this tar file and then trying to run this Valgrind?
Yeah.
Okay. So here we'll be getting a number of lines here, right? So what does this stand for? Here we are talking about 4 different types of accesses. We wouldn't care about I, which is corresponding to the instruction, whereas the rest of it, the L, the M, and the S, which is going to be the data load, data store, and data modify, such instructions we are going to deal with in this assignment. So if you encounter I, you need not bother about that. We'll only talk about these 3 different types of instructions. So it's explained somewhere here that if you have a store or a load, it's just going to cause one cache hit or a cache miss, right? Whereas if it's going to be data modify, it's actually a data load followed by a data store, right? So you can have, it's double the time of L or S. So you could have or you could have 2 hits, or you could have a miss and a hit plus a possible eviction. By eviction, I mean when the least recently used algorithm comes into play, right? When there are so many lines, but you want to bring one more line, you would evict a line to accommodate the new block. Okay. So we have given you a number of trace files in the folder called traces. So right now this example is talking about yi.trace. So in this is how the instructions look like. So we have loads, stores, and then data modify instructions. So I think I skipped this. The data format is going to look like you would have, whether it's going to be an IM, L, or S, and then you would say the address right here, and then you would indicate the size. So that's going to be a standard format that you're going to look at. And yeah, for this assignment we are going to follow a 64-bit memory address system. So far we've been looking at 32 bits, so keep a note about that. So it's been given a couple of files. If you unzip the star file, you would have csymref, which is basically, it's just for you to find out what should be the answer that you would get when you run your program. For example, we are saying, if we are going to have all these parameters for this, what is going to be the output? So it would dump all of this to your terminal. So this finally is going to be the answer, and this is what your program should do as well, right? So csym is the program that you have to write, and csymref is the reference executable that's given to you. So how do you come up with all these misses and hits? So as you know, if you look at this flags here, S is going to indicate the number of set bits, right? So the number of sets is going to be 2 power S, and then we have E, which indicates the associativity, which is the number of cache lines per set, and then we have B, which is going to be the number of block bits. So 2 power B would give you the block size. So starting from right to left, you would have B bits, S bits, and then T bits. Is that right? Okay. And -T would indicate which trace file you're going to play with. So if you go to the traces folder, let me actually go through that. So if you go to the traces folder, you're going to have a bunch of trace files, right? So we are going to talk about yi.trace, which is going to be a couple of instructions like this. What was it called? CSYM. Okay. So let's look at this. You have B, which is 4 bits. So the last 4 bits is going to indicate which byte in the block it is. So what is going to be your block size? So block size here is going to be 2 power B, right? So it's going to be 2 power 4, which is going to be 16, right? So your block is going to be 16 bytes long, and then you have -E, which is going to indicate your associativity, which is just going to be 1 line per set, right? So for each set, you have just 1 line in set. And then S is going to indicate the number of set bits, which is 4. So how many number of sets do you have in this example? 2 power 4. 16 sets. Okay. So now we are going to look at this address, right? As I said before, we are going to have it as the operation, the address, the size. So the second one in this is going to be your address. So 10 is going to look like 1010, right, in binary. So that's the last 4 bits. That's going to indicate the byte number in the block. And what is the set number for this? It's all zeros in the front, right? 0 0 0 0 0, and then you have 1 0 1 0. So the set number is going to be 0. And why is it a miss? This is a cold miss, in fact, because there's nothing in the cache right now, right? Then you go to the next operation, and then you see the address is 20, right? And for 20, would it be in the first set or in the second set? 20 looks like 10100, I believe. So it's going to be in set 1. The first one was in set 0, this is in set 1. It's a different set. So you would have a miss, right? But given that M is a load followed by a store to the same address, you would have a miss first because it's not there in the cache. The second time it would be a hit because you brought it the first time when you did the load, right? And next again you have L, which is 22. So this would be a hit because this was already brought in when this was brought in, and this 20 was brought in, right? So this is going to be the same. So how do you know that? You try to match the set number is the same, then you try to match the tag number, then you see if it's valid. So after you do all those checks, you find that it is the same as this, so you would say it's a hit, and so on. Notice that M can have up to 1 miss, 1 eviction, and 1 hit. Why is that? So whenever you have a miss, there is a possibility that there can be an eviction along with a miss, right? Because if the cache has enough space to occupy that block, you would have just 1 miss. But if the cache has no space, you should evict an existing block and bring in a new block. So you would have a miss plus an eviction, right? So you should take note of that. All right. So let's actually go to. Right. Yeah. You would have a miss and then an eviction. That's how you're supposed to print that. All right. So that is actually being printed by csimref, right? So I think what you guys have to print at the end is just this. The sample output should look like this. So I don't think you have to bother about doing all this. So you don't have to support the verbose mode actually. So you don't have to print, which caused which miss or whether it caused the hit and so on. You just have to finally give the sample output. That's it. So it's just the number of counts. So here you have like 1, 2, 3, 4 misses, and then 1, 2, 3, 4, 5 misses, and then hits 1, 2, 3, and 4 here, and then 1, 2, and 3 evictions. So you just print the total number of misses and evictions and hits. That's it. So there are like 1, 2, 3, 4, 5 functions, out of which I guess 2 are already done for you. This replay trace as well as print summary. So the rest of the functions you guys have to write from scratch. So init cache is basically going to allocate the data structures that would store information about the sets and the cache lines in the set, right? So you'd be using malloc function that you learned before, and that would depend on S and E. So I think we have already given you the code to parse all of these flags. So what you have to do is set a global variable S and E to be equal to 2 par S and 2 par B for the block size. E is just directly given to you. And then replay trace, it almost has most of the code, but you just need to write 3 more lines in that. So that basically is like what calls you need to make to access data. If it's L, what call do you make? If it's an S, what call do you make? If it is an M, what call do you make? Right? If it's an L and S, how many calls do you need to access data? Just 1. But if it's going to be an M, you would need 2 calls, right? Because it's a load followed by a store. So that would help you finish that up. So next, if we look at access data, so this is where the actual code would come in. So this is going to be the longest piece of function that you would write. So here you're going to keep track of the global variables hit count, miss count, eviction count. So this is where you would update all of this. So yes, we saw before you have to follow the LRU policy. Then in the free cache, this should be pretty straightforward. You just free up all the mallocs that you did before in init cache. So that should be easy. Then print summary is already done for you. So print summary basically gives the statistics of whatever. I think I'll show you that. Let's start with main actually. So here we are parsing all the flags that we have: SEB, trace file, print usage. Okay. So just getting the missing command line arguments, not bother about all of that. Yeah, so let's come to, so this is where you're going to call the init cache, and the replay trace would actually, where is that? Yeah, the replay trace would actually read all of the file, whether it's the yi.trace or whatever .trace, and then it would try to go through all these instructions SLM and try to call the relevant function, which is access data. Access data. Okay. And then finally you would call free cache. So you don't have to modify anything in main. Now coming to print usage, this is the statistics that's being printed. No, this is print usage. Print summary is this. Was it somewhere here? Yeah, I think this is defined in another supporting file that we gave, not in this. Okay, I'm not bothered about that. Let's go to init cache. So that's the first call that's made by main, right? So init cache, it's going to allocate using malloc all the data structures that you have to hold for the sets and the cache lines. So here we're going to use the structure cache line T, which is defined here. So if you look at this, we have something for valid bit, which is 0, which is going to be 0 or 1, and then we have the tag bit. The tag bits will be collected into this particular variable. So both of this together form the cache line, right? So you can actually leave it like this, but if you want, you can modify this cache line to indicate any extra variables that you might want to support, for any support that you might need in this program. For example, you can implement a cache which is set based, or you can implement a cache that's going to be linked list based, right? There are two different approaches. So if you're going to use a linked list based approach, then you're going to need something like the next pointer to traverse the lines in the set. For example, if you have 4 lines in the set, how would you traverse through each line? You would go to the first line dot next, the next, and next, using the next pointer, right? So if you're going to use a linked list approach, you might want to use this. If you're going to use an array based approach, you just you can just leave it like this. Or if you want to use any other variables, for example, for least recently used, you might want to use a variable to keep track of number of times that cache block was accessed or something, to find the cache block that has the least number of accesses, for example, right? I would say in linked list you can circumvent having that variable, because every time you access a particular cache block, you can bring it to the front of the list. So you know that whatever you are accessing recently is at the front of the list, so the least recently used one would be the one that's at the end of the list, right? So you could do that, or you could keep a count to keep track of which block is the least recently used. But then for that, you would have to go through all the list of blocks in that set to find out which count is the least, or whatever it is, right? oh, it's not least frequently used, it's least recently used. Yeah, so I don't think that applies. So, yeah, never mind. Okay. So this one, so each set has many lines, right? So we are going to have to type def your pointer to the line as a set for easier, easier programming. We just name it as cache set because one set is going to have multiple lines, and then the cache itself is going to have multiple sets, right? So pointer to the set is going to be type def as cache t for just for simplicity of programming here.
So, would you make like a list for each set, or would you make like a big linked list for everything for all the stuff?
So right
I can't visualize it.
yeah, so this is basically like the same diagram that we had here, right? So we have multiple sets like this.
Right.
So each set is going to have multiple lines. So this set is going to be a pointer to
all of the ones. It'll start at the top.
yeah, and then you can use this lines next to go to this lines next to go to this. So in that case you would have to add an extra variable here called struct cache line star next to that. Okay, so did we cover? Yeah, so these are the global variables that are used, which is like the S, B, and E that you are going to set from the flags in the command line. So S is going to be 2 par small s, B is going to be 2 par small b, and yeah, the global variables for miss count, hit count, and eviction count. So you'd modify all of this in your access data function. So if we go to init cache, yeah, so I think this is why we jumped over there. So it uses the struct cache line t here. So you want to malloc the size of cache line t times the number of lines, which is going to be e, right, for each set. So you'll do that logic over here. So initially you would have to do a malloc for the set itself using the set pointer that we had here, which is cache set t, and then in each cache set t you would have to allocate for each line. So for linked list you can decide to do it dynamically too, instead of allocating everything up front. Okay, so implement the least recently used. So in the init cache you might want to set your tag bits and your valid bits to 0, right? Initially that's going to be all zeros. Anything else that you guys need to know? I think that's about it over there. Free cache is going to be pretty straightforward as well. As I said before, just free all of the mallocs that you have done in your init cache. And then access data is the meat of this project. So as I said before, if the block is already in the cache, you would increase the hit count. If it is not in the cache, bring it in the cache. You have to increase the miss count for missing it, and then increase eviction count if the line is evicted, right? So if we look at the replay trace, I think this is the piece of code that you have to fill in. So these are just the calls to the access data function. So based on if it's S or L or M, you have to call the access, you have to decide the number of times that you have to call the access data function basically. So if you look at the replay trace function, it's basically opening up the vi.trace or whatever trace file you pass in the command line, and then it's going to go through each line in that trace file. If it's going to be S or L or M, it's going to scan the address, the length, and so on. So if verbose mode is set, then it would start printing all the instructions, but you don't need to print out, just the final solution is what you want. Yes, this should just be like 3 lines, that's it over here. So majority of your code would go in access data. So as long as you understand the logic behind searching, which I said is, first you would try to, you can add supporting functions here, right? You can add supporting functions to find the set number or the tag number from the address that you passed in here. This address is nothing but the numbers we saw over here, like 10, 20, and so on, right? So you can write separate functions to extract the tag bits, extract the set bits, and so on. And so you would just call that on this address, and then that would return you the set number. And you would go through all the sets or the lines in the set to match your particular tag bit and your set bit, and then check if it is valid. So if you're going to bring in a new block, you would set it to be a valid block, right? And then once you match your tag bit and the valid bit, you would increase your hit count or your miss count in such cases, corresponding cases. And then in eviction count is something you have to keep track of. For example, in linked lists, if you're doing a linked list implementation, you could let's say you could have a variable to keep track of how many blocks you have passed through till now, so that you know how many number of lines have already been allocated in this particular set. So if it is above capital E, then if it's less than or equal to less than capital E, it's fine to allocate one more cache block. But if it's already equal to E, you should sort of remove the least recently used one and then allocate one more, right? Bring in one more block. So as I said again, you could choose your way to implement it. So if it's a linked list, you can choose to bring it to the front each time, every time you access it, so that you know the least recently used is at the end of the linked list, or something of similar idea. That's totally up to you. So this function does not return anything. Everything is going to be directly printing the global counts, that is the hit, miss, and eviction count. So it's easier for you to know if you're going wrong, because we have given you all the trace files that we'll be using to test the program. So we are not going to test on additional files. So you can basically, we have also given you the answers. Basically, you can compare it against CSIM-ref, right? So you know what the answers you have to expect. You can get that. So of course, we'll be checking your code to see that you have not hard-coded any information there. So it shouldn't be like, because we've already given you all the test cases, we'll be looking to make sure that you guys have written the actual logic.
Wait, you're only specifying these subcases?
Yeah, so the traces folder has like, I believe, 6 files. Yes. So that's because you guys are turning this on 14th of May, right? That's the deadline, and then we have to release the grades on 15th. So we just want to give you the choice of having, so you would basically know your grade before you turn in your assignment.
That works for me.
Yeah, so there is a program actually called TestSim. Did we talk about that here? Yeah, TestCSIM. So if you run that, it would compare your program against the CSIM-ref. CSIM-ref is the reference file and CSIM is your file, so it would tell you how your implementation compares. So if you have that right, then you would get full marks on your assignment. So that's just to make the grading easier, so that we don't have any regrade request after that, as we're going to plan to release the grades then. Yeah, it should be a pretty straightforward assignment than the P5 or whatever it was. So.
So the TestSim just compares
Mm-hmm.
Okay, so they don't need to like individually do each of them, you can just run that.
Mm-hmm. Any other questions?
When you find the least grades for P5 and P6?
All right. Let's talk about this because I'm recording this right now, so I would have to stop when I'm finishing done with this. So if you have any more questions on P7, otherwise I'm going to stop it. Okay.